I welcome Dr. Yosi that he joined us today for this webinar. And this Center of Medical Informatics and Healthcare, which is actually associated with the Department of Biotechnology and Bioinformatics. And this is the second webinar in series. First was by our Honorable Vice Chancellor, and the second is by now Professor Yosi. And the coincidences both are from the same area, that is biomedical and related fields. So this is just, I would like to, before Dr. Yosi begin with his webinar, I would like to tell you within 2 minutes about the brief of this department. This Department of Biotechnology and Bioinformatics was established in the year 2002, and we have undergraduate, postgraduate, and PhD programs in the department in the field of biotechnology and bioinformatics, which is like BTech, MTech, MC, and the doctoral programs. And also we have our postdoctorate student also can join this department. This department is having research in various areas, whether you talk about environment or infectious diseases or bioinformatics, drug delivery, healthcare, plant tissue culture, animal tissue culture. There's a versatility among the 17 faculty members that we have in the department, and a very strong network of our scholars, BTech and MTech students. So this department is giving a lot of various courses and also give freedom to the students to choose their electives. And I could see the Professor Yosi's seminars today in that direction, that if the people feel that this field is an interesting one, so they can choose the electives, they can choose or their research area in this particular field. And you might have seen, if the center website, in this center website, there are faculty members from all across the departments, whether it is biotechnology and bioinformatics, electronics also, physics and material science also. So we strongly believe in the interdisciplinary research projects and a teamwork from all the departments of JUIT and also from the other institutes. So with this introduction, again, I would like to request Dr. Tirath and Dr. Ragini that they can carry over with this seminar, and very warm welcome to Dr. Yosi that he is today with us with a very good topic and with his research work. Thank you so much and welcome again.
Thank you very much, sir. For your informative words. Now, I would like to tell you that we are having a wonderful response from all over the world, and in this, I can see more than 100 participants, and many international participants are already there in the list. Sylvia is there, and many others are there, because we have got registration from Canada, USA, Poland, Ukraine, Hong Kong, Bhutan, Indonesia, Bangladesh, Philippines, Pakistan, Nepal, Algeria, Amman, Nigeria, as well as some other countries. So it's a very good response from all over the world. And now I would like to tell you that this center is striving for the excellence, not only in research and academics, but we are organizing workshop at national level. We will plan an international workshop in near future. We are having this international webinar series, and we are planning to have various other activities. Various research activities are also going under the aegis of this center, because we are having hybrid BTech and PhD works under the aegis of Center of Excellence. Now I would like to call upon Dr. Ragini to introduce you first about Yosi's excellent profile, and then we can have his talk.
So good morning, good afternoon, and good evening to everyone. Today I, Dr. Ragini Raj Singh from Department of Physics and Material Science, JP University, welcome one and all for the second and very important talk of this international webinar series. Today's talk will be delivered by Professor Yosi Shechem Diamand. We are pleased to welcome Professor Yosi from Tel Aviv University, Israel. It is my privilege and enormous pleasure to introduce Professor Yosi Shechem. He has many credentials in his credit and having a very long and rich experience in teaching and research. His research is in the field of micro and nanoelectronic science and technology, specifically electrolyte splitting of metals and alloys. interconnect technology for ULSI circuits and flexible electronics, and electrochemical biosensors for the food, medical, and agro applications. Presently, Professor Yosi Diamand is the Bernard L. Schwartz Chair for Nanoscale Information Technologies in Department of Electrical Engineering, Physical Electronics, and the Department of Material Science and Technology, Faculty of Engineering, Tel Aviv University. He is also a visiting professor, CNR IMM, Rome, Italy, and Waseda University, Tokyo, Japan. A distinguished international chair professor, Fengchia University, Taichung, Taiwan. Endowed chair professor and director of the TAU TIET Food Security Center of Excellence. He served in many academic positions, including being the academic director, Microtechnologies Laboratory, Director, University Research Institute for Nanoscience and Nanotechnology, Head of the Department of Physical Electronics, Vice Dean of the Faculty of Engineering for Industrial Relations, and with the Friends of the Faculty in Israel and abroad. He is on the University Board of Governors, in University Patent Committee, Head of the Industrial Affiliation Program, Faculty of Engineering, and a member of the Board of Directors of Ramoth, that is the Technology Transfer Arm of Tel Aviv University. He is a member of the Magnet Committee promoting basic and generic technologies in Israel, the Innovation Authority, Ministry of Trade and Industry. He has published more than 260 journal papers, more than 400 conference papers in registered proceedings. He has 33 patents to his credit, 7 chapters in books. He edited 2 conference proceeding books and 2 books separately. I just gave the short introduction as he has done so much that is very difficult to say in this short time. Now I would like to invite Professor Yosi to deliver his talk. Today he will be sharing with us his expert opinion on the very essential topic, that is flexible sensors for biomedical applications. With that, I ask you all to give full attention to Dr. Yosi and helping me in welcoming him for today's talk. I am sure this talk will be advantageous and informative for all the participants. So before the start of the talk, some important announcements for the participants. Write your queries in the chat box. Your queries will be answered at the end of the presentation. I request all participants to make sure that your microphones are mute. The feedback link for the e-certificates will be provided at the end of the talk. Write your name and affiliation in the form as you want on the certificate. So now I request Professor Yosi to please begin his very important and imperative talks for the participants and for all of us.
Thank you very much, Ragini. Am I audible?
Yeah.
Good. So I'm switching to opening the screen. Just a second. Can you see my screen?
Not now.
Can you see my screen now?
No.
Is it okay?
Yeah.
Good. So today I will talk about flexible sensors for biomedical applications. And Ragini, I'm switching for the next slide. Is it okay? Can you see the presentation? Is it okay?
Yes.
Good. Okay, so Ragini saved me time to see all my credentials, but I'm also, since last year, also an endowed chair professor in Tapar Institute of Engineering and Technology. So I would say until last March, I used to be there every month and even visit Shimla and JP University, which you did not mention, but we have a memorandum of understanding with you. So I hope to see you soon again. I really like to visit India. This is my second home now. And as you can see from my credentials, I am from the School of Electrical Engineering, which means I'm an electrical engineer. I work on developing technologies. So I develop technologies for many applications, including microprocessors and sensors. But today I will focus on our work on biomedical microsystem technology, flexible, and I will answer why flexible. I'll give you some examples. In the second part of the talk, I will mention some work on what materials people use for biomedical applications. I will speak a little bit about agriculture and food, because in the last 3 years, I found out that many technologies which people use for biomedical applications can also be used for agriculture and food, especially flexible electrodes for agro application and post-harvesting applications. I will not cover all electrode fabrication methods, because this can be just the whole semester. I will just tell you about few new technologies, which is laser processing and nanoparticle supersonic cluster beam deposition, that we collaborate with the University of Milano with Professor Paolo Milani, and some conclusions. So this is the content for today. And without further introduction, let's ask what are biomedical flexible sensors, which are practically mainly non-invasive, although some more work is being done on invasives that can detect disease or symptoms of disease by detecting the composition, deficiency, or abundance of specific constituents in the subject of interest, like skin, saliva, blood, pressure, tear, urine, neural activity, and more. So practically, I work on the field, and in my lab, we make electrodes, for example, and we make sensor for more than 20 years. And we are interested in all sorts of materials. And the key problem, I'm going to show you today the key problem. They're relatively simple devices. We just have a little bit of metal on plastic, and you can think this is it. The problem is that nothing is simple in science and technology. And we talk about signals from the body, and I took it from a beautiful review that was published recently in 2020 on flexible inorganic bioelectronics. You talk about electrophysiological signals, you talk about physical signals, you talk about biochemical signals. You also have a photoelectric signal, like, for example, all this PPG and blood oxygen, blood pressure. And you have all this, you can see a long list of possible signals. And each one of them, you need to tailor the specific electrode, the specific sensor. So when we talk about biomedical applications, and you can see to the right, you are following a certain physiological parameter. For example, on the hand, on the head, or any other part of the body. And today we talk on signals, but we also talk on actuation, like, for example, monitoring drug delivery, do some electrical stimulation, and also maybe some therapy and computing. And of course, you want to transfer it to a computer and to do some, today is very sexy to do artificial intelligence, deep learning, all this. But you want to do analytics on the data. You want to analyze the data. And in order to analyze the data, you need a lot of data. And flexible sensors are on the body. And why flexible? And this is, like, for example, I took it from the same review, a schematic illustration of flexible inorganic electronic devices that are intimately integrated with human tissue for EP signals measuring. For example, EEG, ECOG, ECG, and EMG. And you can see about it. You can do ECG, put the electrodes here for the ECG, for sensing the EMG, the electromyograph. You can put it over the shoulder here, or if you want to do EOG or ECOG or ECG on the brain. And the flexible, these are the signals that people measure. And the advantage of flexible, you can see immediately. At flexible, they can sit, what we say, conformally on the skin or on the body. Conformally means sensor takes the shape of the body. So the key in flexible sensors is, can we make them as conformal as possible? And I'm going to show you later, there is some problem if the sensor is too much conformal, there is some problem. It's that you need, like in any engineering problem, you always have some compromise. So what are the challenges and the strategies? And they were summarized so nicely in this paper. You have the compatibility. If you look at if you make sensors, the challenges and strategies for flexible, stretchable devices on human body, you have the mechanical issue. You want stretchability, comfort, contact. For example, if you are using a wearable and you are an athlete and you're using to monitor your body and you're running a marathon, you need it for 4 hours to sit nice in your body. You don't want it to scratch or itch or even cause some problem. You have skin-like stress strain behavior. And the strategy here, for example, to stretchability, you do structural geometry design. Comfort, you make it very, very thin and microstructure substrate, make it small. And skin-like device, you are limiting the strain, you do use a strain limiting substrate. The other aspect is the biology. For example, being breathable, for example, using textile, micropores, nanofiber, mesh membrane-based substrate. You want to be biodegradable, tunable, degradable substrate, and resorbable functional materials. And no rejection. You want inhibition of bacteria, for example. We use silver. We started to use it 20 years ago. I think even Ragini was familiar part of our effort to deposit silver as an antibacterial material. Encapsulation with biocompatible material like PDMS, hydrogel and silk protein, nanoparticle, nanowire-based substrates. The other issue is thermal and thermal management. When you need some thermal conductivity substrates or heat sinks, so there's a type of it. So again, why flexible? And you can see everybody talk about flexible telephones and flexible electronics. First, the other advantage of being flexible, it's robust. It does not break. I mean, you can have other problems, but if it falls on the ground, it doesn't break. You can fold it, can be adjusted. Also usually lighter because most of the polymers, their specific gravity is less than metals, and also can be environmental friendly using green materials. And this is a very important issue because if we are successful in microelectronics, we're using billions of devices, and the waste is a big issue later. So again, why flexible? And we talk today about flexible sensors. The whole field of flexible electronics is a very big field. But we talk today about flexible sensors only, which are mechanically compatible from hardness and robustness. They are biocompatible, for example, using carbon-based substrates, chemically compatible. You want to functionalize them using organic chemistry. So we can do, since we are using organic-based or silico-organic-based materials, we can do a lot of chemical modifications to the substrate, make them compatible, make them conducting, doing a lot of things. We talk about a specific section on the flexible sensors are wearable. By the way, not every flexible sensor is wearable, but wearable is a very important section on the skin, for example. This I took from one of the recent papers. You make a whole device, attach it to the screen. This is an electrode array and a wireless device. Also implanted devices. And the implanted can be very large, relatively few millimeters or a few centimeters. Also, for example, very small. This is a paper that published recently when people insert carbon nanotube sensor inside a target tumor. So this is also a flexible sensor made of carbon nanotube. Then actually pick up a signal from the tumor. I will not go into detail. This was published very recently. So if you look at the landscape of all future electronics, you have the classical electronics. You have the transparent electronic. This is for display. But the transparent electronic, we can also make it stretchable, flexible, and for example, textile. And we can use it for biomedical applications. But you can see from this overlap that the same technology that people develop for display sometimes can be used for biomedical applications or vice versa. And this is what we do in my group. We develop technologies, and sometimes we use it for biomedical application, or I would say most of the time. But sometimes we also use them for displays and sometimes for electronic circuits. And the advantage is that we can put the electronics with the biomedical device on the same structure. Now, the next generation flexible electronic systems and the key relevant sectors, this I took from a relatively older review from 2012 of Professor Arokia Nathan, and this was published in the IEEE about 8 years ago. If you talk a whole flexible system, the materials, nanowires, nanotubes, graphene, silicon, silver, etc., everything I mentioned before. And people use it for display, using for energy storage, for textiles, for human interactivity. And today I will focus on the healthcare. But as you can see, everything is related, which means if you are developing, my advice to you is based on my experience, if you work on developing flexible devices for biomedical engineering, or you please read papers also on displays and textiles. It's a lot of other relevant information coming from completely different disciplines. And the wearable sensor is, I would say, the more sexy regime people are talking about. Even I cannot see me, but even I have a wearable watch connected to my cell phone, which can measure temperature, pulse rate, position, motion, hydration, still not gas and pressure, but glucose is the next generation, and you can put it on the body. And why? I think it's pretty obvious. All of you which are in the biomedical field, a very important issue is for the elderly. It's the aging society. If you look at Europe, Japan, countries which have relatively the society growing older, you need to have sensors to monitor, because early detection of problems can save a lot of trouble from the person, for preventing medicine, for identifying problem. And you want it also, the other aspect we discuss is we want to make it compatible with all these communication technologies, because we make all these sensors, but we want to transfer them through the internet to the clinician, to ambulance, family. And when we develop sensors, we have to remember it's a part of a system. It's not just the sensor. And we have to bear in mind that we don't want, let's say, we don't want to develop a sensor and find after 2 years of work that it's very difficult to connect it to the internet. Sometimes there's no choice, but also for young people or the young in their spirit, runner, you can measure, for example, you want to measure a physiological signal, transfer them. People talk about remote medicine. I mean, you can put the sensor, the physician can see you and he can see him using virtual reality. And today, when I have to tell you from my personal experience, today after all this issue of the COVID-19 virus, in my country, in Israel, a lot of the physician visits are virtual now. And there is a very strong need, and the company and the local healthcare companies are starting to bring more technology. For all, I don't need to explain to you what, if you can solve problems remotely without personal interaction, especially for the elderly, if you don't want them to go to the hospital or to emergency room, you want them to be isolated. A lot of parameters you can do using all this technology, and the key is sensor. At the end of the day, if you don't have a sensor, everything doesn't matter. You can have the best interconnect, the best internet, but if you don't have the sensor, you are doomed. For the skin, mouse, prosthetic, and implants, your healthcare, you use all this motion recognition, knee motion, voice, pulse, one healing monitoring, breath monitoring, prosthetic monitoring, human-machine interface. And again, I stress, all of this is connected to the computer, connected to some sensor. You need, that's why I put here with, you have the healthcare issue, but also AI and human activity monitoring. Everything is important. Another very good paper that was published 2 years ago talk about the physiological biosignals in the human body and corresponding healthcare sensors with user interactive systems. If you are making a flexible sensor, they can interact. They can actually be part of the interaction. So you can take physiological signal during motion, measure pressure, motion, tactile. You can get thermal signal. You can make electrophysiological signal, and everything you can transfer to remote clinical device, and you can do self-diagnostic. You can even think of a lot of the things you can use AI, some deep learning mechanism to identify problems, and the home healthcare in the future, we anticipate some of it to be, of course, we need physicians and personal contact is important, but many problems can be solved using this. So if you look at the morphological control of micro nanostructures sensing materials, and I took it from the same paper, first you'll talk about dimensional materials like nanoparticles, nanowires, nanosheets, and nanopores. And there are 0 dimension, 1 dimension, 2 dimension, 3D materials. And from the biomimetic structure, you can make materials which are whisker-inspired, spider's crack-inspired, skin-inspired, hierarchical structures. So when next I'm going to talk a little about materials. And one of the advantages of using flexible materials that we can shape them in very, very interesting structures, and we can integrate them with a lot of materials. Now, typical sensors, and again, I use this wonderful paper, saves me a lot of time when I present this to my students. What are the mechanisms for flexible devices? For example, you can use resistivity, and I'm going to show you materials, and this is, for example, you take an elastomer, PDMS, polydimethylsiloxane with carbon nanotubes. My group, we mix it with gold nanoparticles, but the idea, you make a conductor mixed with an insulator, and when you apply pressure, they change their shape, and when they change the shape, they change the resistivity. So you can use resistivity monitoring, or you can put them between electrodes and measure the capacitance, and change in capacitance give you indication on the change of position. You can use piezoelectric materials. We also use in my group. Here, this paper represents zinc oxide. My group, we use organic piezo materials, like PVDF, similar materials, but it's the same principle. And another material which is recently has a lot of publications is triboelectricity, which means, you know, the tribology is the science of friction. Because of friction, you are generating electricity. So this will allow you to identify lateral forces and shear forces. So with all these sensors, we can identify pressure, motion, friction, position, etc. So, for example, give you a few examples before we go to what we do. For example, this is a recent publication on a stretchable hybrid materials, and they mention all sorts of possibilities. You can make metal nanoparticles and nanowires inside the polymer, or carbon nanomaterials inside the polymer matrix, or conducting polymers like polypyrrole, polyaniline, PDOT, and similar materials, and sometimes mix them with the nanoparticles. And recently, and I have to tell you that I'm following these papers, which is a very new topic. It's called liquid metals. Metals, there are some metals like gallium and gallium alloys, which are liquid at room temperature. And you can integrate them on polymers. And you can make a beautiful contact, because this is a liquid. And the liquid is absolutely conformal, can take the shape of the structures. And you can ask, how do I monitor the shape? So you can encapsulate it and bring it in contact with what you want to do. You just have to make sure that it will be confined. So you can look at the stretchable hybrid materials, or you can look at geometry. For example, if you want to make something flexible in the X direction, you make it, instead of a straight line, you make it like a serpentine. Or this is some serpentines. Or you can make it with wrinkles. If you make it wrinkled and crumples, then the material can bend easier. You can make a nanomesh or a mesh structure. So if you break some wires, you still have conduction. Or you make it porous structures. So this can bend because it's very flexible. So all these strategies of making hybrid materials, or making some geometry design, or a combination, people use them, and there's a lot of papers on this. And every combination has advantage and disadvantage. And I think that there is not going to be one winner. There are going to be many possibilities. Okay, so materials and processes. We talk about polymers. So when we talk about sensors, we talk about substrates. Substrate is what we make, what the sensor is on a substrate, can be a polymer. And a polymer can be hard, like polyimide, nylon, or similar, or elastomer, like polydimethylsiloxane, which are PDMS, which is software or similar materials. Or other, like photodefinable polymers, ionic polymers, paper, fabric. And I'll talk a little bit about ultra-thin silicon. If you take silicon and make it very, very thin, it's flexible. And this is a very interesting direction. And I'm going to show you some examples. We don't do it, but we follow it because the major problem to make it, it costs few, I would say you need a fab to make silicon CMOS, and it costs a lot of money. And we don't have it in the university, but some institutes like IMEC in Belgium and other places, it's an interesting technology, which I'm going to show you today. And sensor materials can be conductors, semiconductors, elemental, compound, conjugate, can be nanoparticles, core shell, everything in any shape and color and type, can be insulators and nanomaterials, and interconnect and packaging. It's also, don't forget, once you make the sensor, make the device, I would tell you the most difficult part, and I'm not joking, is how to interface it with the rest of the world, how to make the interconnect and packaging. I'll tell you, my students struggle. They make beautiful flexible sensors. They put them on plants, on leaves, and then how to connect it to the computers. You have to make all these itsy bitsy tiny wires and make the interface, and you have to invent an interface. And it's kind of a stupid problem, but it's a very serious problem. And these are the materials that we use. For example, polymer for biosensor. This is the paper I showed you before. I showed you this application, and they're using this polysulfide network obtained via 3-ethylamine TA catalyzed thiolacrylate click reaction between this very long name material. So you can see that people are designing the special polymers to have some very special structure. So there's a lot of material science involved in developing new polymers, new materials for flexible biosensors. Other materials, for example, if you want to make electrochemical sensors, you need electrodes, reference electrodes, metal, semiconductors, metal oxides are very common, zinc oxide, indium oxide, other materials, and more. It's a long list. So here are some more examples. This is another paper published in 2017. This is a non-invasive sweat analysis. And this is one of my students, one of my ex-students, she did a postdoc on this topic, and she was working for a few years. And you can see you have a waterproof band, the kind of plastic. You have some glucose sensor, electrochemical sensor, pH sensor, humidity sensor. And for example, the glucose sensor includes silver chloride reference, platinum counter, porous gold, and the Nafion ionic polymer on top of it. And you can see that this is a classical device material issue problem. And on top of it, everything has to be flexible. And I'm going to show you later what are the mechanical problems when you actually make the structure. Now I'm going to, we don't do it, but I'm going to show you a little bit something which is really, it caught my mind recently, because all this CMOS technology, you take a silicon device and you just make it very, very thin. And because it's very, very thin, you can put 3D chip stacking, mechanical flexibility, ultra-thin chips. Ultra-thin chips, and let me switch. It's called, by the way, this technology called chip film. It was published first in 2009. But the idea, you take a silicon wafer and just make it very thin. This is it. And 20 micron silicon, you can see how between fingers it can bend. You can force it into radial structure. You can make it with a mixed signal. This is a complete integrated circuit. And this is the beauty of this technology. It's just very expensive to make yet. I mean, everyone is very cheap, but you need like more than $100 million, I guess, at least to build the facility, sometimes more. But you can put a complete, on this area, you can have few millions of transistors and signals. So you can make the whole system on a chip with the electronics and everything. And you can make it, for example, they make it like a smart monitoring system with an RFID tag. And this is, I would say, one of the technologies to follow. It's not as flexible as polymers. It has its own problems, but the advantage, you can put a lot of electronics, so you can think about this technology as, I'm sure people will find good applications for this. Nanomaterials. This is a review, very recent review that published this year. We talk about carbon nanomaterials, polymer materials, and other materials, and you can see the electrochemical sensor, gas sensor, DNA sensor, everything. People use nanomaterials, and I'll skip this slide. One of the advantage, and we work a lot in nanomaterials in my group, we developed zinc oxide and nickel oxide nanomaterial-based electrodes together with Professor Salva Mirabella from University of Catania. This is a classical electrochemical sensor. You put nanomaterials on top of it, but then you bind to them. For example, you bind antibodies, antigen to detect, this is, for example, the ELISA chip. So you can use carbon nanotubes, graphene, indium tin oxide, nanowires, metallic nanoparticles. We use a lot in my group, indium tin oxide and zinc oxide and nickel oxide. And we bind to them all this biological material to make the sensors. And the advantage of nanomaterials that you can, a very large surface area, very small size, you can use them as a binding post for all this biological material. I will not go through all details of this slide. I just want to show you a few more slides before I'm going to the rest of the talk, a flexible integrated sensor array for multiple perspiration. You can think, and you can see that practically all the devices, they have these electrodes and they integrate them. This is a glucose sensor, you have the electrodes and you sense it. This is a biofuel cell. They actually have, all of them have similar structures. And this is another example of a schematic illustration of the process. Here they use iridium oxide, hemine, titanium oxide biosensor. This kind of structure, they also put the nanomaterials, and this is the cell. And I think this is my last example, and I just show it because this is something similar to what we do. We do a lot of electrochemical sensors. So naturally, this talk, I will give you more examples on electrochemical sensors, but I don't want you to get the wrong impression. There is a lot of work on optical sensors and other sensors. Just because of the limited time, you talk about the electrochemical sensors, we want to do something like cyclic voltammetry and measure the, again, I'll skip this slide, and let's go now about something more specific about flexible electrodes. As I told you before, you need the flexible electrodes for two major applications. One, there's a whole part of what we call electrochemical sensors. You need flexible electrodes. But even if you make optical sensors and other sensors, you need interconnect to the optical devices. You need the interconnect part, and the interconnect, they have to be also flexible. So you use polymer substrates, conducting electrodes, and the reference electrodes. And we have a lot of problems. Delamination, adhesion of the materials, cracking is a big problem. And today I will talk a lot about cracking. And metal on polymers. It's very easy to say, I put metal on a polymer, and I'm going to show you the problems. There's a lot of work, like gold nanoparticles in polyester, cracks in gold in PDMS that was published. You can see that even 17 years ago, people talk about the problems. And the idea, you put metal on polymers, and today I'm going to talk about metal on polymers for biomedical sensors. So the challenges are the following. First, the patterning issue. since we deal with structures which can change their shape, also they can be non-planar. Now, the problem here is most of the people use projection lithography. They use photolithography to pattern microstructures. The problem is that they are using a projection systems, and they have a big problem of defocusing, which means you cannot do lithography on a non-planar structure. You have the issue of the photoresist. When you do photolithography, the idea is practically you make your design, you take a big camera, you project your image on the device, and you do the process. The problem is that all the lithography is using polymers, and your substrate is also a polymer. And it's also very difficult to make the compatibility that one material will not affect the other material. So there's a lot of patterning issue in flexible sensors. It's very complicated to do the patterning. It's very difficult to do polymer substrate and a polymer lithography. You have material problems, material with different families, like metal on polymers, and you have a big mismatch in material physical properties that might cause very big reliability issue. So what are the solutions? What are the research frontiers today in making flexible electrodes? One is metal printing. Can we do a metal inkjet? All of you, or most of you, have an inkjet printer, but you are printing ink. Can we print metal ink? Can we use conductive polymers, carbon nanotubes, graphene? Our presentation is metal on elastomers, which is what we discussed today. So our process, what we develop in Tel Aviv University in collaboration with the University of Milano, is flexible electrodes using femtosecond laser ablation on thin metal films on polymers. So what I'm going to do now, I'm switching from the large overview of the field until now I gave a 35 minutes of review of the field of flexible electrodes. I describe all the materials, and in the next 20 minutes, I'm going to talk about what we do, how we solve the problems. And one of the biggest problems that everybody faces is metal failure due to cracking. And next we show that patterning flexible electrodes using femtosecond laser ablation and the origin of the crack. In order to solve the cracking, and I will explain you why there is cracking and how to avoid the cracking, how to make reliable sensors. So first, one of the technologies which is very promising now, and many people doing it, and we bought this system a few years ago. We are taking a laser, and this is a femtosecond laser. We're using the 343 nanometer wavelengths, which is ultraviolet. We're using pulses, approximately 270 femtosecond pulses. We have a galvo scanner, so we can scan with the beam. And we use, first we prepare the substrate, then we do surface treatment and cleaning, then we put the metal, and then the laser beam is ablating the metal. So I'll go quickly. First, we take the PDMS. PDMS is the polymer, is an elastomer. And the way it's not going to be a class in material science, but the way to make this polymer, you buy cross-linker, you buy the monomer, you mix them together, wait 24 hours, you have the polymer. So we can control the composition. For example, 1 to 10 is very much used, but I'm going to show you later that the reason I'm showing you this slide, because we can control the mechanical properties of the polymer. And this is going to be a big, big issue. Next, we clean the surface, oxygen plasma. Next, we put titanium and gold on top of it. This is our new evaporator. And then what we do, you have a substrate with gold and on titanium on the polymer, and the laser beam is ablating the polymer. And the nice thing is the following. In these wavelengths, the PDMS is transparent, but the gold is absorbing. So we can pattern, and because it's a femtosecond, there is no heat diffusion. And because it's a very short time, it's a very short pulses. The pulses are as I told you, it's about 270 femtosecond pulse. So because the time is so short, we have a huge huge energy density per unit area. So the ablation sometimes is so fast, so the rest of the substrate does not hit. And because of that, we don't have a damage to the polymer under it. I'm going to show you later the structures. Practically, let's focus on this part. If you have a nanosecond pulse, this is the laser pulse. You're heating the structure, and the heat, this is the red zone, is propagating. If you have a femtosecond pulses, you are ablating the material, but the heat is not, because the time is so short, the diffusion length of the heat, which is square root of D diffusivity times time, is so small, it's maybe a few angstroms, so there is no heating, only ablation. And because of that, we get much, much cleaner cut and much nicer structures. And the first generation, this is the structure, gold on titanium and PDMS. And I'm showing you, to show you a very important issue. The material, they have their hardness. The Young modulus, sorry. The Young modulus of gold is 80, and thermal expansion is 14.2 ppm per degree Celsius. The PDMS is 10 to the minus 6, 10 to the minus 3. You see a huge mismatch in the Young modulus, in the mechanical properties. And you can say, this is very soft material, who cares? Nothing will happen. This is gold, gold is strong, gold is hard. This is a mistake, and I'm going to show you later. So what we got is, this is the electrodes we make by the laser. You see this is very clean definition. These are the pads, 1, 2, 3 pads. These are the working electrode. This is the auxiliary here. This is the reference electrode. And this is after we cut it and clean it and we use it. And we put the 3, you see, this is students' interface, 3 crocodiles. You can do better. The problem is, when you look very close, this is what you get. When you deposit gold on PDMS, this is what you get. On regular PDMS, you can solve this problem, don't worry. It's the new generation, this was the first generation. So we say, oh, what should we do? Different deposition method, different materials, maybe change profession. No, so one issue, we say, let's try to see if we have another technique. So we looked at we have a laser, and there is a technology called lift. And lift is the following. You take the glass, you put a glass, on the glass you put the metal. And then you are illuminating from the back side with a laser. And because you're illuminating from here, you are generating a drop, and the drop is going down and deposited on your substrate. So you go to a different point and deposit another drop. And then deposit another drop. And then you can make an electrode. So this is called lift. And because we have a laser and you're taking your substrate, it's called a donor. And from the donor, you are generating metal drop. This is like an inkjet printer. But instead of having a cassette, we have a substrate of glass with gold. And we put drop, 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 drop. We can put more than 100,000 drops per second. And you can put many drops, you can take many beams of the laser, so you can work very, very fast. And this is a commercial product. There is an Israeli company called Orbotech. They make this device, and they actually very useful devices. So this is how it looks. These are the electrodes on the soft polymer on PDMS. And this is how it looks. You see no cracking, no nothing. It's really get very good results. But you know, we are university, anytime we solve a problem, then we look for another problem. We still have this problem of cracking of the normal process. So we clean, we etch, we catalyze the seed, we do electrolysis plating on top of it. And electrolysis plating on top of it solves a lot of the problems because we can do some combination of a softer material, but we still had some cracks. This is electrolysis deposition. And by electrolysis deposition PDMS, you see we got no defects, but we still want to understand why we get cracks in the old problem, because we really like to do evaporation on plastic because it's commercial technology. So we looked at the modulus of tungsten as a definition of the crosslinker. Remember how we make this polymer. We take a crosslinker, mix it with the monomer, heat it, wait. And we look at this table and we saw, well, we can control the Young modulus of the polymer between 1 to 10 megapascal by controlling the crosslinker. And let's see what happens. And surprisingly, when we do 1 to 2 ratio, no cracks. We still have wrinkles, but no cracks. 1 to 19 ratio, we got beautiful cracks. So we want to understand why. How come this very soft polymer with the modular Young of 10 to the minus 3 gigapascal is breaking, making cracks for the gold, which is more than 10 gigapascal. So we took the structure. This is another experiment. We put some, we try to be smart. So we put between our polymer and the metal, we put another polymer called parylene with the modular of 1, which can between 80 to this. Still got the same cracks. So we say we need to solve this problem. So what we do, we are engineers, we do mechanical analysis. I will not give you the whole structure, but we are doing all the calculation of the forces in the structure. And we write a code, everybody can use it. We published this in a paper recently. That we can calculate the stress in this material, and because we want to deal with more than one layer, we develop it. This can be polymer metal. So we solve it for multi-structure. And then we apply this solution to we calculate the stress in our materials. So this is stress versus depth. This is a PDMS, about 5 microns. And as expected, the stress in the PDMS is very, very small. You see, it's less than 10 megapascal. But then, to our surprise, we got in the gold a stress of more than 300 megapascal, huge stress on the gold, which we did not expect it. And what we found out that PDMS is a very soft material, but it's uncompressible, it's not compressible. And the problem is the gold and the PDMS have different coefficient of thermal expansion. So when you heat them and cool them, the PDMS is applying a huge force on the gold. And this is gold. This is the CTE of gold. This is Young modulus of gold. This is the Poisson ratio. So this is the problem. PDMS is a huge coefficient of thermal expansion. So we need to reduce the coefficient of thermal expansion of the polymer. So one option is to switch to Kapton. It's less flexible, but with much, much less coefficient of thermal expansion. And we did again the calculation and found out that for Kapton, the stress is only 13 megapascal, and the stress dropped significantly. And just to give you the mechanism of cracking, if you have a PDMS, you put on top of it the metal, and when the device is cooling down, this is applying a force, and you have this something called wrinkling. It's a non-linear phenomena, and this is the critical stress for wrinkling. This is taken from a textbook, and these wrinkles, when they break here on the bottom of the metal. And this is the critical stress for PDMS is 0.2, and for Kapton is 18.9, which means first, what we found out that if we deposit it on Kapton, no cracks, no nothing. Or alternatively, we change the composition of the PDMS to increase the Young modulus of the PDMS and to reduce the coefficient of thermal expansion. And then we solve the problem. So we developed a whole system to make, not only to make electrodes, but to analyze when they break, when they don't break. And we have a table, everybody that wants to use metal X on a polymer Y, we can predict beforehand if it's going to crack or not. So this is our contribution, that we can forecast for any combination of any metal, that we know the properties, if it's going to crack or not to crack. So this is our conclusion. And the origin of the metal film cracking is the difference in the coefficient of thermal expansion. And also the elastomer is soft, it applies enough stress, and Kapton can serve as a substrate for flexible interconnects. And a combination can be, you do a Kapton substrate, and then on top of it, PDMS and then metal. And the femtosecond laser ablation is a good technology. And thin film stress analysis is a very efficient tool when developing components that are assembled of different types of materials. The last topic I want to talk today is a very new technology, which is extremely, I think it's very promising. And it's a combination of nanoparticles and PDMS. And the idea is the following. This is called supersonic cluster beam deposition. There are a few systems like this in Europe, and we had a huge research program with University of Milano, a Catholic University in Leuven, and University of Birmingham, and other universities. And because they have the tools, we don't have the tool in Israel, so they make the devices, they make the samples for us. We focus on biomedical devices, and the idea is to take a source which is called cluster source, and you are generating nanoparticles of metals. And these nanoparticles can be 1 or 2 nanometer in size. You accelerate the nanoparticles, and you shoot them into your PDMS. Remember, PDMS is your flexible substrate, and you want to make the flexible device on the substrate. So you put gold into it. And this is how it looks. This is a supersonic cluster beam deposition. This is PDMS, the polymer. And you can see if you implant enough gold, this is the PDMS with gold nanoparticle. It's a composite material, porous material. It's approximately 50% gold, 50% PDMS. But you can see that the gold, and you can even make it more. And what happens, this is a very, very flexible material. And the gold nanoparticles with low energy and neutral electrical charge are implanted in PDMS. The nanoparticles concentration provides ohmic conduction together with PDMS stretchability. And actually, there's even a company now in Italy making and selling this technology. And the gold nanoparticles are synthesized by technology called cluster source. And a set of aerodynamical lenses are collimating the cluster beam, and the gold nanoparticles penetrate the PDMS matrix. And this is the constant, we can actually, Professor Milani is measuring resistance as the actual thickness of the gold, and you can see that initially the resistance is very, very high. This is ohms centimeter. This is very, very high. When the gold film is this is 100 nanometer of gold. If you have less than this, the resistivity is huge. It's almost not infinite, but giga ohm and more. Above 100 nanometer, the resistivity goes down from 1 kilo ohm centimeter to 10 to the minus 2. The resistivity goes down by 5 orders of magnitude. And you can use it, by the way, to measure position and to measure stress. And then it becomes like a gold deposition. So if we deposit 200 nanometers, we can have a good electrode, and it's because it's flexible like PDMS and conducting, not like pure gold, but 10 to the minus 2 is a pretty good conductor. And again, we use gold, the laser processing. It's simple, no mask, no lithography. Students can do the design at 8 o'clock in the morning and have the device at 9 o'clock in 1 hour and test it. And this is the devices. And by the way, you can see here that we use the monomer and the PDMS with a relatively high CTE, so we got cracks. But the good news, the cracks, we have gold. Even though we have cracks, all the devices worked, because we have, the cracks are only on the gold on top of the PDMS. The gold inside the PDMS are still conducting. This is top view, this is the cross section. And this is how it looks. This is a better sample. This was I showed you good samples and also bad samples. This was the first run was a lot of cracks. Second run was actually much better. And this is the laser processing. And we can go down to 3 micron lines. And you can see this is a 3 micron electrode. This area here is called HAZ, heat affected zone. I told you there is no heating, but there's a little bit of heating. So this heat affected zone is about 1 micron. So we can make 3 micron electrodes. Usually we don't need such electrodes. Most of the devices are 90 or 160 microns. This is how it looks. And just to show you that we have a working devices, we make electrodes with different widths, measure the resistivity, and this is 1 over resistivity versus electrode width, and we proved Ohm's law. We proved that this is Ohm's law, resistivity proportional to 1 over the width of the device, and we calculate the specific resistivity, and you can see here is it's about 2.6 10 to the minus 3 ohm centimeter, which is excellent for electrodes. It's not good. Pure gold will be 3 orders, so 3 orders will be like 4, 5, 10 to the minus 6. But this is like polysilicon, this is like indium oxide, this is like zinc oxide. It's pretty good material, pretty good conducting, and very, very flexible, really very flexible. So to summarize this talk, and I promised Ragini that it will be between an hour to hour 15, so we are close to the end of this talk today. The interim conclusion about what we do is soft and flexible microelectrodes were fabricated by integrating a novel metallization and patterning process. And we can go down to 3 microns by laser microprocessing. And the microelectrodes fabricated by the supersonic cluster beam deposition and femtosecond laser have the conductivity to act as electrodes. We use it for plant sensing, but Professor Milani is using it for electrodes for the brain and electrodes for the skin. And there's a lot of applications for this technology now being investigated. Now, if we summarize the whole talk, what I talked about it today, I started with overview the field, and then I showed you what we do. And we have other projects, but because of time constraints, I focused on what I would say the most hot topics. By the way, what I showed you recently was accepted to the material conference that I'm going to show this presentation in October in the material conference in Europe. It was accepted for oral presentation, which is very respected because they accept, I think, 1 out of 10 papers. So I'm giving you like a sneak preview on the MAM conference this year, the Materials for Microelectronic Conference. And the other paper on the stress was accepted to this conference also, but only to poster presentation. And the flexible, but if you go back to the topic I talked about it today, is flexible microsystem technology is available for biomedical applications. So if you need something, you can do it. You just need an access to a clean room and to manufacturing facility. In Tupper University, we don't have it. I'm also visiting very often BITS Pilani in Pilani, and they have a very nice facility next to them where they can make nano electrodes. And I hope in India, people will have more and more clean rooms, more facilities. India is a big country, and you should have a technology to make electrodes, flexible electrodes. There's a lot of technology, but also a lot of interesting science. What it includes electronics. I did not talk today about flexible electronics, but you can also do electronics. Actually, I talked a little bit when I mentioned the thin silicon, but it also includes sensors and actuators. I did not talk today about actuators, but you can do drug delivery, you can make ultrasound transmitters, you can do some things. Optics. A lot of the sensors measuring using light to make a wearable device. Even the watch I have in my hand has a monitor using LED-based monitoring. There are many promises in biomedicine, and the number of applications is growing rapidly. And there are also a few commercialization successes. And for example, one section of flexible sensors or flexible electronics is what we call biochips. And the biochip industry today is more than $20 billion. So it's not a small industry anymore. But more research is needed, especially in new materials, nanoparticles, core shell, in their integration, how to put them, how to deposit them, how to make them reliable, reliability issue, and also, if you want to put it in vivo or to make it wearable, it has to make sure you don't cause any damage. So there's a lot of regulations about it, and packaging is also an important issue. So I would like to thank you and thank to my team, and this presentation from the thesis of Tali Dotan, Yelena, which Ragini, I believe you remember Yelena, and Itan Turgeman, this was their thesis. And this was supported by the Ministry of Science, Israel Science Foundation, and the MANA Center for Global Challenges for Food Security. Thank you so much. Okay, this is the end of the talk.
Okay. So thank you, sir, for this wonderful and very imperative and informative talk. I think all the participants benefited with this talk. So now I will ask some questions on behalf of all the participants. So the first question is from Utkarsha Srivastav. She asked, what can be the possible disadvantages of wearable sensors?
Of what sensors? Wearable sensors.
Yeah.
The advantages are clear. I mean, you can see me. See, I have the wearable device on me measuring for athletes. The advantages is continuous monitoring, because you wear them, you can use it continuously. You don't need to come and disconnect. And because it's wearable, companies are investing a lot of electronics. Like in the wearable I have here, you can think about it. You have the sensors, you have the pulse sensor, oxygen sensor. You have all the electronics, Bluetooth going to your cell phone, going to your physician. So the big advantage is continuous monitoring. By the way, there's one disadvantage which people did not expect. And I hope, I'm going to tell you something, I have to check the truth, but one of my friends in America told me that when people start to have all these wearable watches, many people are going to an emergency room with a panic attack. I mean, they say, my pulse is 180, I'm going to die. People, the problem is people is misuse, or one of the, I will not call it disadvantage, but I would say one of the problems of wearable is education of the user, how to use this information. We are scientists, we are using to bad measurements, but many people take everything seriously, and they should. But the main problem is the main problem, and there's another issue of privacy of people. You don't want all this information to be on the cloud. So if you suffer from something, your insurance will not give you insurance, and the government will not give you treatment. Privacy is a big problem. You see, this is like Facebook and all this. Once you have this innovation, you start to run into unexpected problems, which are social. I'm not an expert in social science. From technology point of view, I think the problem is like any developing of a new measurement system. You want how to make it error-free, how to make small false positive, how to make false negative, and to make it reliable. And this is a big challenge, which in many cases I'm not sure can be solved. I mean, people have to live with sensors. It's very difficult. Wearable, it's if you're wearing it in the morning, it's not done by a physician in a hospital or by a nurse. You always have this chance of a bad measurement. So this is one of the biggest problems. So if we can solve it, if you can make a wearable device with a 0.99995 error or correct, you will be a hero. This is a big challenge.
Okay, sir. So the next question is, when we talk of wearable sensors, especially those that are inserted in the body to monitor a particular disease, do these sensors need to be manufactured to be personalized for that one person specifically?
Excellent question. I would say this is so excellent question that I don't have an answer. because this is exactly the problem. These people are debating, people are asking, should we make it personalized? And you can do it personalized. You can think, because of the laser printing, you can even do 3D printing. You can actually design a sensor, and we spend some time, for example, if a person has a tumor, we take the negative of a tumor and we can print a sensor which is exactly the size of the tumor and flexible. It can grow with the tumor or shrink with the tumor, hopefully. The problem with this is cost, efficiency, and again, how to make it right. And much easier to make a standard electrode. And for example, another example, I know people which are developing electrodes for the brain, for the cortex. And the question, should I make can I make the electrode to fit exactly the fine details of the cortex, or can I make an electrode which is not exactly, but I have so many sensors can compensate by signal processing? I did not answer your question, but I just want to tell you that your question is one of the challenges for flexible electronics, and it's also a conceptual challenge. What direction to go?
Okay, sir. So next question is from Sukhmani Dua. Do these wearable sensors, basically the inserted ones, can have some side effects, or body can take it as foreign body and can respond showing some side effects?
Yes, definitely, and we are afraid of this. And definitely, thank God there is FDA and regulations, and I believe you can have like any implantable. You have the mechanical effect, you have the biological effect, you have the chemical effect, and we have to be very careful. It's very easy to monitor to short-term effect, but it's sometimes questionable and problematic to identify long-term effect. You don't want to implant something and to find this is a disaster after 5 years. This is going to be, it's a big problem, it's a big issue. And I think this will be solved if will be better information exchange between countries, between FDA and other places. We want to make, if somebody in other countries has a problem, we want to know it beforehand. It's very important to distribute the problems also. Universities are usually doing it very well, companies not always. But I think this is it's going to be a big problem. It's a big problem. It's a big problem.
So next question is from R. Surekha. She is asking, do the wearable sensors leaches inside our system after or during its time of validity?
Usually not. Leachable is a very, we try to make it from materials which will not leach. For example, my first sensor was silicone in the blood. We made some sensor for implantable device into the heart, and then we found out that silicone is etched by the blood. So it's not leaching, because we usually make the sensors from materials which are inert. Like if you make gold electrodes, gold will not dissolve in the body. Or if you make a polyimide, it will not leach. We are worried about fouling, about interaction, side reactions. If I can try to understand your question, leaching it will be related if we do drug delivery and we have some excess or something, but we are not there yet. But again, it's a problem we try to solve it by using the right choice of materials.
Okay, so sir, the next question is from Toshi Singh. She is asking, can the printed circuits be recycled or reused by any method?
Do you understand? Can we recycle the devices?
Yeah.
We try, listen, if it's personalized, we try not to recycle it. We try to make it personalized, and after use, we just need to make them, we want to make the waste gracefully. We don't want to make the waste material will cause environmental problems. I don't think that physicians like to have recyclable electrodes, but you know, if you use I think even today EEG, they throw them away after you use them, even the cheap electrodes. I don't know. I think that in bioelectronics, if it's implantable, I think it will never be recycled. Outside, I'm not sure, but I have to tell you one last thing. My work in India, we make the sensors. We try to invent them. We try to make them very cheap. We are looking for strategy how to make low-cost sensors. And microelectronic sensors are very cheap. The cost of the physician, the cost of the nurse, and the cost of the hospital is usually more. Microelectronics can be made very cheap. The people sell these electrodes at very high price or making implantable device very expensive, but this is not because they are expensive, because they have to cover all the development, and it's a business issue. But recycling, I doubt it. Recycling of the final materials, yes. If you have gold electrodes, you throw them away, then you are separating the gold from the plastic and use the gold again. This is what we do. We recycle the materials after use. Yes, this is what we do.
Okay. So, sir, the next question is from Archita Sharma. She's asking that about polymer substrate. What type of polymers have been used? Natural or synthetic polymers? What is their modulus value of chosen polymer substrates?
Listen, if I have time today to give you the list of all polymers, we are going to finish by 10 o'clock at night. There are so many polymers. And I try to, you see, in my lecture, I put like soft polymer and hard polymers. But some people synthesize the polymers. And natural polymers is an excellent choice. I know there's one of the top group in the world in Kottayam, Professor Thomas and the other groups. There are some excellent groups in India. And I think natural polymers is an excellent choice that should be pursued. Tissue-like polymers, etc., etc. Hardness from megapascal, in hydrogels, it's even kilopascals, up to Kapton, which is 2 giga. It depends on the application. If you put sensor for the bones, you don't need it to make very soft. If you want to sensor for the skins, you make it 100 or 10 megapascals. The beauty of polymers, you can tune their strength and hardness and surface and everything. They're wonderful materials. But again, I cannot give you an answer about what is the most popular. I would say that PDMS is popular, polyimide is popular, nylon is popular, and there are many other popular. SU8 is polymer, PMMA is, again, I will stop here.
Okay, so the next question is from Dr. Santosh Patra. He's asking whether any sensor to identify COVID-19 virus?
Oh, there are many sensors. I think I can point today on 10, many people develop sensors. Even we also developed sensor for COVID-19 because we had, in the last few years, our zinc oxide, the nanoparticle polymers, we developed a sensor for RNA and DNA. We had the project for detecting DNA and RNA in mycoplasma in milk with Italy. And it's very easy to translate it to COVID-19. To make a sensor for COVID-19 or like any other virus, once you know the protein or once you know the DNA, you can either make a sensor for the protein or sensor for the DNA, RNA. And they're very specific, and you can do RT-PCR, which is expensive, but you can make electrochemical impedance spectroscopy, electrochemical. There are a lot of publications. I would say that making a sensor detecting viruses is not complicated. One of the problems of these viruses is the capsid. They are the viruses inside the capsid of protein. You need to break it, but people know how to do it. To integrate everything on a chip, this is the challenge, and some people are publishing about it now. Now you take the sample, you break it, then you analyze it. And people publish now, the recent publication now from an American publication about doing it from the saliva. So the answer to your question, yes. What to do with it, I don't know. And of course, the regular issue, error rate. What is false positive, false negative? But the answer, I think detecting COVID now is a problem which is technology possible. It's now how to reduce cost, how to make it more reliable. It's not that we don't know how to do it. We know.
Okay, so next question is from Professor Sudhir. He is asking, can we take out gold from waste printed circuit boards to make gold films?
Yes. But to take gold from printed circuit boards to make sensors? Yes. I mean, this is what we do also. This is the question?
Yeah.
Oh yeah, you can use, by the way, you can use PC. If you don't have a expensive facility, you can make beautiful electrodes using PC board technology. They're not so flexible, but they're very low cost. And you can change the substrate if you can allow it, replace instead of using a FR4, which is the polymer, the epoxy glass composite, change it for Kapton, and you can do it. You can take a PC board company and convert it to make Kapton-based electrodes. We do it. We actually have a company in Singapore doing it for us.
Okay, sir. So now I'm asking the last question for the session because of the time constraint. So this question is from Rajeshwari Thakur. She's asking, after insertion, does sensor contaminate with any type of microorganism?
We try to avoid it. You have to, for implantable devices, there are very, very strict rules of how to do it right. You don't want to implant it with contamination. So you have to follow regulations of implants. You know, this is you have to make it sterile. You have to do everything according to the right way. I mean, if you're asking if to do it outside, like ambulatory treatment or in the field, this is a different issue, and there's a whole field of flexible technology that we have some effort in for the military, for defense, because if you want to take care of a soldier in the field, you don't care about some bacteria. You have a problem to solve, you solve the problem, then you send it back to the hospital, then it's taken care of. So there's a whole field called emergency biomedicine, where you can compromise on the, I would say, on the cleanliness, because you need to solve a problem of injured person, accident or something. But your question is an excellent question. It has to be regulated, it has to be done in the right way. And of course, everything has to be sterile, has to be right, because every time you implant something, the nightmare of the situation is that you have some pathogens inside. This is really, can be a disaster. So it's a good point that you have to make sure that all these implantable devices, we work more not on implantable, we work on wearables. So this is less, you have the skin, so this is less dangerous. But your question is should be very approached carefully and taken care of.
Okay. So thank you, sir, for the very, very explainable answers. And I think all the participants have some benefit from this talk and your answers. So now I will call upon Dr. Teejraj Singh for vote of thanks.
Thank you, Ragini. And thank you, Professor Yosi, for wonderful talk and very informative session. I hope everybody, including us, have enjoyed it. Just wanted to share the news with you that next webinar from the Center of Excellence, we are planning it on 9th of October this year, 2020 at 11 a.m. It will be delivered by Head of the Department, Professor Sudhir Kumar. And the topic is very interesting because nowadays we are having lots of electronics in our daily life. So it will be electronic waste and healthcare. So very interesting topic. We will send you the link and all the details. So we will be meeting again on 9th of October. But before that, I want to share a few things, especially with Yosi, because Yosi, you already visited us many times here in India. We were with you for almost 3 years in Israel. And you know, recently, the 12 beautiful campuses of India, you have seen our campus, one of the beautiful campus of India. JP University is also being included in the top 12 beautiful campuses of India. And we are already having an MOU with Tel Aviv University. So that we are going to pursue for a longer period of time. And I am sure your expertise and the expertise from Tel Aviv University and the whole Israel is always with us. As an Indian, being the JUITN, we are always expecting positive aspects from your side also. So thank you very much for being with us, enlightening us with your excellent knowledge. Thank you very much, sir.
Thank you so much. Thank you. I hope to see you soon. Thanks.
Okay, thank you everybody, and see you on 9th of October then. And goodbye till then.
Okay, bye. Thank you. Goodbye.
Okay.